Section 3.4 in chapter 3 is called power. In this course, when you're done, I want you to be able to know the difference between terms like power and energy. But just a basic definition of power, power is the rate of doing work. Now, section before this, when we talked about mechanical work, we defined work in terms of joules, but power is the rate of doing work. Okay, so as we look at our associated figures with this, and I'll dial this in for us, and we'll go through a really good example that will explain this to us, and actually will be our first look at an actual motor. So it's about time, right? Since this is a machines class. So here we are, and we're going to define this term called power. So to begin doing that, let's write down equation 3.4. Power is work. Work is in joules. And as you can see in your textbook, and of course it doesn't come off very well in my drawings here, but this is a cursive italics W that is the symbol for work. And then, so we're going to make this really confusing. This power is measured in something called watts, which we've heard watts before. And again, I can't really make the distinction here as I'm drawing these things, but you can see in the text that there's a distinction, or the way that those two W's are drawn. One is for power in watts, and the other is for work in joules. And the final part of this equation, and that's not the best looking T in the world, is it? Okay, is lowercase t, which represents time. We're in SI units, so that is going to be seconds. The unit of power is the watts. We also often use kilowatts or megawatts when we're talking about power systems. And one thing too that you ought to commit to memory is this idea that horsepower is so common in our vocabulary that even though it's not SI measure of power, it's something that we're still very used to. And so sometimes we will, we'll be given that the power of a motor is in horsepowers, and all our calculations are done in watts. But for our purposes, 746 watts is equivalent to 1 horsepower. And that's something you ought to just kind of commit to memory. That's something that you ought to know. All right. And then in the text, he also mentions, this idea of where this term horsepower came from. And it's actually an old term that corresponds to the average power output of a dray horse. Okay, a workhorse. All right, so let's put this formula to use. He says that an electric motor, and here is our first electric motor that we've actually viewed. This electric motor, through a pulley system, is going to raise 500 kilograms of mass 30 meters. Now, we've done that before when we defined work, but now what we're going to add to this, and the power equation does this, is this time component, okay? So what we're going to do here is we're going to raise this in 12 seconds. So, if we think about a motor application, maybe there's some process or there's something going on where, that rate of it being raised could vary. Maybe another application needs it done in 5 seconds. Maybe another one doesn't require it for 20 seconds. But what we'll see is the time involved determines, or is a major component of, the size of the motor needed to do it. Okay? So anyway, that becomes a part of it. So in this particular case, on 500 kilograms, that's our mass. Our height is 30 meters. Now, if we go back to this equation for work that we talked about earlier, You know, we had force times distance. Well, we still don't, you know, we could start using that to get this part of our um, equation, but there's a problem, is we still need to apply our initial equation that defines force as 9.8 times the mass. Okay, so for a lot of these problems, you start there. So it's 9.8 times the mass of 500 kilograms, multiplied out, and he says in our textbook that that is 4,900 newtons. Okay, that's really what you would call part one of this. The 4,900 newtons we can put in this to determine the work. So the work done is 4,900 newtons over a distance of 30 meters. And so the work done with that multiplied out is 147,000 joules, or we could call that 147 kilojoules if we wanted to. Now, this is the work. We're also given the time. So now we're actually ready to apply our equation, and I'll try to write that up here, where I'm going to say 147,000 joules divided by 12 seconds. And that is going to come out to be 12,250 watts, 12,250 watts. And a preferred way to write that in an engineering notation would be 12.25 kilowatts. And so that is the actual power. It's the rate of the work. Okay, it's the rate of the work. And if I, for instance, wanted to do this in 5 seconds, then if I looked at that problem and say, hey, I want to lift this 500 kilograms in 5 seconds. Okay, well, I change this to 5, and then I'm going to get a different answer, of course. And let me get my calculator out and we'll see what that was. 147,000 divided by 5 comes out to be 29.4 kilowatts. So if I wanted to raise this same mass quicker, I'm going to need more motor, or I'm either going to require that motor to do to output more power one way or another. One thing to look at. And you know, depending on the application, that motor may be under spec to do that. All right, now let me wrap this one up. The final thing that we wanted to look at here was do this conversion, where from our original answer here at 12 seconds, where we had 12.25 kilowatts, we want to know how many horsepower that is. Okay, so that's 12,250 watts. We've got a conversion. It says 746 watts is equal to 1 horsepower. Okay, watts are going to cancel out. 12,250 divided by 746 says that we would need a 16.4 horsepower motor to do that. Now, for me personally, I'm still more comfortable in thinking about motor size than horsepower. But again, what I may have to do is I may have to convert back and forth between horsepowers and watts, because all our equations are given in SI units. All right, so that finishes section 3.4.